Welcome everyone, I'm Dominik Tornow. I'm founder and CEO of Resonate. Building modern cloud-native applications is characterized by its inherent complexity. At Resonate, we focus all of our efforts on reducing this complexity. Our goal is to make modern applications dead simple. Dead simple to understand, dead simple to develop, and dead simple to operate. We are developing a distributed programming and execution model called Distributed Async Await, an extension of Async Await that makes distributed programming a first-class citizen. Distributed Async Await is based on open specifications, and our implementation is entirely open source. I began my career in the United States as an intern nearly 20 years ago, in 2006. That year was not only pivotal for my professional life as a software engineer in Silicon Valley, but also pivotal in the history of cloud computing. In March 2006, AWS launched S3 and in August EC2. Since then, the number of cloud applications and therefore distributed applications has exploded. So for the past 2 decades, I focused on concurrent and distributed systems. Now, I work on building distributed async await by day and authoring my book, Think Distributed Systems, by night, both with the goal of making distributed systems accessible and dead simple. Today, every application is a distributed application. Think of mobile applications, think of cloud applications, or think of microservices. The question is no longer whether an application is distributed, but only to what extent an application is distributed. Today, distribution is a fundamental aspect of software engineering. This shift has enabled unprecedented scalability and unprecedented reliability, but has also introduced daunting complexity. We have to deal with the added challenges introduced by fragmentation, by computations that are distributed across space and time. A computation is distributed across space when the same logical computation spans multiple physical computations concurrently, that is, at the same point in time. A classic example is the fan-out, fan-in pattern. In this pattern, we divide a task into subtasks, process subtasks concurrently, and then combine their results to produce the final result. A computation is distributed across time when the same logical computation spans multiple physical computations sequentially, that is, at different points in time. A classic example is the chaining pattern. In this pattern, we divide a task into steps, process steps in sequence, with the output of one step potentially serving as the input for the next. Distribution across space and distribution across time introduce challenges that can be traced back to 2 defining characteristics of concurrent distributed systems: partial order and partial failure. The defining characteristic of concurrency is non-deterministic partial order of executions. In a concurrent system, we simply do not know what will happen next. The defining characteristic of distribution is non-deterministic partial failure of executions. In a distributed system, we simply do not know what will fail next. So let's consider a simple example. 2 processes, P and Q, each consisting of just 3 steps. The concurrent composition of P and Q leads to 20 distinct possible executions. The distributed composition of P and Q leads to 69 distinct possible executions. Now imagine the behavior space of real-world distributed systems with dozens or hundreds of processes, each with dozens or hundreds of steps. As distributed system engineers, our task is to ensure that a system behaves well, even in the face of non-deterministic partial order and non-deterministic partial failure. In other words, we need to design systems that maintain correctness even in the face of grueling uncertainty. Now, this table presents a conceptual framework to reason about the challenges introduced by concurrent distributed environments and the countermeasures we employ. Concurrency introduces non-deterministic partial order. And to mitigate the uncertainty introduced by partial order, we employ coordination. Distribution introduces non-deterministic partial failure. And to mitigate the uncertainty introduced by partial failure, we employ recovery. Now, ideally, we would write distributed systems using simple, normal code, just functions. Functions are the universal abstraction for computation, and they compose recursively. Even our largest systems are built from the smallest building blocks, functions. So functions embody the quintessential programming model, offering an ideal developer experience. They're easy to write, easy to read, and in 2 words, they are dead simple. So now this is the story of Distributed Async Await, a programming model for building concurrent distributed applications that offers a delightful, dead simple developer experience based on functions and promises. But dead simple is not just a catchy phrase. Dead simple is at the center of our technical values. Dead simple to understand, dead simple to develop, and dead simple to operate. Now, Distributed Async Await is an extension of Async Await. Async Await is a popular concurrent programming model that is the bedrock of many popular languages and runtimes, such as JavaScript, TypeScript, Python, C#, or Rust. Async Await formalizes the concurrent structure of non-distributed computations, but does not concern itself with recovery. In contrast, Distributed Async Await formalizes the concurrent structure of non-distributed and distributed computations and does formalize their recovery. Let's consider a simple example, a URL summarizer. The application accepts a list of URLs and concurrently summarizes each URL before returning the result. To summarize a URL, the app fetches the content of the URL and subsequently summarizes the content via an LLM. A non-distributed implementation with Async Await and TypeScript is arguably dead simple. We iterate through the list of URLs, invoke download and summarize URL, and await the completion of the resulting function executions. Download and summarize URL first fetches the content and subsequently summarizes the content with an LLM. Async Await formalizes the concurrent structure of the application, here illustrated as the resulting async call graph. Local invoke and local await relationships are first-class relationships. However, fetching the content of a URL and subsequently summarizing the content with an LLM is an expensive operation, so we may want to distribute calls across multiple nodes. A distributed implementation with Resonate's Distributed Async Await for TypeScript is arguably just as simple. We iterate through the list of URLs, invoke, download, and summarize URL remotely and await the completion of the resulting function executions. Download and summarize URL first fetches the content and subsequently summarizes the content locally with an LLM. As mentioned, Async Await formalizes the non-distributed concurrent structure of an application. However, across processes, relationships are no longer formally handled by the runtime. Instead, we manage them ad hoc, often via HTTP calls, via message queues, inventing brittle proprietary protocols, basically on the spot. But Distributed Async Await formalizes the non-distributed and distributed concurrent structure of the application. So both non-distributed and distributed invoke and await relationships are first-class relationships. And additionally, distributed async await formalizes recovery. If any subset of the async call graph fails, distributed async await restarts that subset and repairs the call graph. Now, since distributed async await extends async await, it is based on the same abstractions, functions and promises. Two abstractions that are well liked and well understood. Functions and promises are composable universal abstractions for computation and coordination. Do some stuff and wait for some stuff. When the caller invokes the callee, instead of waiting for a result, the caller immediately receives a promise while the callee executes concurrently. A promise is either pending or completed, more specifically resolved or rejected. If a promise is pending, the promise is unfulfilled and the execution is still ongoing. And if a promise is completed, the promise is fulfilled and the execution has concluded. Now, resolved indicates success and rejected indicates a failure. Now, caller and callee are able to coordinate their execution, with the caller waiting for the promise and the callee completing its promise. Now, given what we know about async await, what extension do we need to make distribution a first-class citizen? We need durable promises. Durable promises are, and here we go again, dead simple. Durable promises have a unique ID, a URL, and store their state in durable storage. That's it. That's all we need. This simple concept forms the very foundation of a concurrent distributed programming model. By assigning a unique ID, promises can be used to coordinate executions across processes. And by persisting its state, promises can be used to recover an execution. So in effect, there is a dead simple programming model, distributed async await, running on top of a dead simple environment, the distributed event loop. The distributed event loop consists of two protocols. The distributed coordination protocol and the distributed recovery protocol. And as the names imply, the coordination protocol is responsible for the coordination between executions, and the recovery protocol is responsible for recovering failed executions. But before we explore the coordination and recovery protocol, let's first explore the environment in which they operate in. So this diagram presents Resonate's implementation of a distributed async await runtime. And there are two different viewpoints to consider, the physical view and the logical view. The physical view divides a deployment into Resonate application nodes, referred to as app nodes or simply nodes, and the Resonate server. Each node is a process, such as a Node.js process or a Python process. And inside each node is an instance of the Resonate SDK, which acts as the interface between function executions running on the nodes and the Resonate server. The nodes act as a data plane, hosting function executions. Now, the Resonate server acts as a control plane, hosting durable promises. The logical view divides a deployment into the application layer, the distributed application, and the platform layer, the distributed runtime. The application layer represents your distributed application, which consists of distributed function executions. Although these executions are physically distributed across nodes, they form one continuous async call graph. The platform layer represents the underlying distributed runtime, which consists of the Resonate SDK and the Resonate server. The Resonate SDK running on every node is responsible for managing remote function invocations and awaiting their result. When a function is invoked or awaited remotely, the SDK communicates with the Resonate server. And the Resonate server coordinates function executions and facilitates recovery of function executions via their associated durable promises. Distributed coordination is handled by Resonate's distributed coordination protocol. In async await, when a caller invokes a callee, the caller does not transfer control to the callee. Instead, the caller receives a promise and resumes execution, and the callee starts execution. Eventually, when the caller needs a result of the callee, the caller awaits the promise. If the promise is pending, the caller suspends until the callee terminates and completes the promise. Zooming in, we highlight the central role of the promise. First, we have the mental model that in the first step, we create the promise, and in the second step, we create the execution. Second, here we highlight the registration of a callback. When a caller awaits a promise that is pending, the caller is resumed when the promise completes. This happens by registering a callback on await. When the promise completes, the callback resumes the caller. We can extend this flow to distributed async await. When the caller invokes a function remotely, the SDK creates a durable promise on the server. The server sends an invoke message to another Resonate app node. When the app node receives the invoke message, the callee starts the execution. When the caller awaits a promise, the SDK registers a callback on the server. Eventually, the callee terminates and completes the promise. The server executes the callback, sending a resume message back to the caller. Finally, the caller resumes execution. So the distributed coordination protocol is based on two messages, invoke and resume. Two messages is all we need to implement coordination. Distributed recovery is handled by Resonate's distributed recovery protocol. This slide illustrates the communication flow in Resonate's distributed recovery protocol, involving three key components: the Resonate server, the pluggable transport, and an app node. As we just discussed, the Resonate server sends two types of messages: invoke and resume. Each message is delivered and processed in the context of a task. The process begins when the Resonate server sends a task's claim URL to an app node via transport such as HTTP or a message queue such as AWS SQS. Upon receiving the task's claim URL, the app node proceeds to claim the task. Now, claiming the task initiates the heartbeat protocol between the app node and the Resonate server. If the app node fails to send timely heartbeats, the server presumes the node has failed. At that point, the server reschedules the task, ensuring recovery in the case of partial failure. When the app node successfully completes processing the task, the node sends a completion request back to the server. Upon receiving this, the server marks the task as finished, therefore guaranteeing that the task will not be retried. So in combination, distributed coordination and distributed recovery guarantee progress in the face of partial order and partial failure, the defining characteristics of concurrent distributed systems. Now, to wrap it up, building modern cloud-native applications is characterized by its complexity. Resonate has one goal: making the development and the operations of modern applications dead simple. The first step towards this goal is a dead simple programming model, distributed async await, based on functions and promises. Now, if you want to chat, if you want to share your comments, your feedback, or your questions, or if you want to get involved, let's connect. Thanks for watching.